Hello everyone and welcome to this lecture. In this lecture, we will talk about one of the most important class of symmetric matrix that we call positive semi-definite matrix. Why these matrices are so important? One thing is the eigenvalues of these matrices are always non-negative. Okay, so either the eigenvalues can be 0 or the plus, and these makes our life super easy. Okay, and we will see in this lecture some examples of it, why the eigenvalues of positive semi-definite matrix are positive, or in fact more correctly non-negative. So there is a class something called positive definite. In that case the eigenvalues are all positive. Okay, so let us start with the definition of positive semi-definite matrix. Okay, very important class of matrix. Okay, great. So any symmetric matrix, suppose A is any symmetric matrix, that means A equal to A transpose, it is called a positive semi-definite matrix if it is called a positive semi-definite if you take any vector x, and do this operation x transpose ax, this quantity will always be greater or equals to 0. Okay, and if it is strictly greater than 0, we will call it positive definite matrix. Okay, now the thing is, I mean, just by this this definition, what is the basically what are the outcome? How can we say? I just say that the eigenvalues of this matrix are positive. How can you say that? It is actually just revealed from its definition itself. So suppose there is some vector v which is eigenvector of A corresponding to some eigenvalue lambda. Okay, then what we can do, let us multiply on both hand side towards left by v transpose. This will be what? This will be nothing but lambda times v transpose v, right? Now what? You see that this quantity v transpose v is always greater or equal to 0 by the definition of positive semi-definite. So this is equal to 0. But now remember, your v is always what? Non-zero vector, right? Because it's an eigenvector, right? So this implies that lambda is always greater or equal to 0. Very simple fact, very beautiful fact. So eigenvalues of positive semi-definite matrices are always 0. Okay, can you say other way? Suppose I give you symmetric matrix and all the eigenvalues are non-negative. Okay, can you say that the matrix will be positive semi-definite? Okay, can we prove the reverse direction? If basically this, if the eigenvalues of a symmetric matrix are non-negative, then we will prove that it is indeed, then it is positive semi-definite. Okay, how can we prove that? How can we prove this beautiful fact? Okay, so let me call this theorem. Okay, and this, as of now, let me call the definition. Okay, so now how can we prove this beautiful fact that if eigenvalues are all non-negative, then in that case this matrix will be positive semi-definite? Recall that I told this many times that spectral theorem will always save us in many occasions. Okay, it will help us in many occasions. Okay, so let us make use of spectral theorem because A is symmetric matrix. Okay, so let us prove it. proof. Suppose A is that matrix. Suppose A is symmetric matrix. Okay. So then in that case, what? Let A be a symmetric matrix. Okay. Be a symmetric matrix. In that case, what we can do? We can always write A as what? A as what? It's basically something called, I mean, you can write the basically we have done this spectral theorem form, right? So it's called orthogonal diagonalization also. So basically you can always write this matrix in this form. Okay, where V consists of what? All the eigenvectors. D is set of eigenvalues, not set, sorry, on the diagonal there are eigenvalues, the corresponding eigenvalues of the eigenvectors, and V transpose, yeah, of course it's transpose, but important thing is V into V transpose is equal to identity matrix because we are orthonormal vector. Okay, very good. But then if suppose it is given that all the eigenvalues are positive, all these Di are positive, basically if I open it, right, so all these eigenvalues, suppose this is called lambda 1, lambda 2, lambda are actually non-negative, not exactly positive, right? So non-negative, so this will be this. So I can actually write this matrix as, if you just take square root of these, because these eigenvalues are positive, right? So I can always take a square root and then again multiply by square root. This is essentially the same as basically doing this. Let me write this, lambda 1, lambda 2 up to lambda n to the power half, okay? And then again do this, lambda 1, lambda 2 to lambda n, and these are 0, 0 guys, okay? So this is suppose again half. You multiply them, this you will get. And this we can do, since these halves are nothing but the half power of the eigenvalues corresponding, and this is V transpose. Okay, now you see that you can always write this matrix as this, V D half, okay, V D half, and then again D half VT, right? Now since these guys are what, basically D half is again a symmetric matrix, right? D half is again a symmetric matrix, so you can indeed write this matrix as this. So basically I can write this matrix as D half times V and then its transpose. Let me transpose of this times transpose, okay, and then D half VD. Okay, very easy to follow because D half is a symmetric matrix, right? Very good. Now what? It is easily follow. Now you can always see that whatever x you choose and do this operation Ax, right? What will be this giving to you, right? Suppose this quantity you can call maybe C, okay? So C, and this is again maybe C transpose, okay, C transpose, or I mean vice versa, whatever you can show. So basically now this quantity will be what? So X transpose C transpose X, right? So now you see that you can always write this matrix as equal to, yeah, this is nothing but C transpose X transpose C transpose X, right? So this is nothing but dot product of a vector with itself, which will always be greater or equal to 0, right? Very good. So now this matrix is also symmetric, positive semi-definite. That means it actually the equality, or what we call, if the eigenvalues are all positive, the matrix is positive semi-definite. If matrix is positive semi-definite, eigenvalues are all non-negative. Okay, sorry if I am saying positive, it should be non-negative. If it is a positive, we will call positive definite rather than positive semi-definite. Okay, very good. Okay, so now you can actually treat this as also a definition because it is a if and only if condition. Okay, so let me write. So let me write this. What? A matrix, symmetric matrix. Okay, symmetric matrix is positive semi-definite, or PSD I will write. So positive semi-definite, and maybe I will use this acronym. Maybe let me write here positive semi-definite, PSD, and then we will make use of this. So positive semi-definite, that means in bracket I will write positive semi-definite, if and only if all the eigenvalues are non-negative. Very good, very useful fact, as we will see. Okay, now so this can be treated as definition either in terms of eigenvalues or in terms of that quadratic form we have seen. Okay, very good. So now what the next thing is, it is important to realize that corresponding to every, so suppose A is positive semi-definite, that means A actually can be written as, this implies A can be written as some C times C transpose, right? It's very easy fact, we have just seen it, right? It comes from the spectral theorem, right? Very good. So always for some C. Okay, very good. So this is important factor, important result for us. Okay, now next we will prove that basically this. So suppose A is a symmetric matrix. Okay, the next theorem is A is a symmetric positive semi-definite. So I will just write as positive semi-definite matrix. Let A be a positive semi-definite matrix. Okay, and as follows. So maybe as, so basically now I want to write the eigenvalues of a bigger matrix in terms of eigenvalues of its some partition. So suppose each partition as this: A equal to basically A11, A12, A21, A22. Okay, now, and where A1 and A22 are some square matrices. Suppose where the partition is like that, where A11 is some P cross P matrix, so that it is a square P cross P matrix. Okay, then what can you say about the eigenvalue, largest eigenvalue of A and the largest eigenvalue of the blocks? Okay, so we will prove that the eigenvalue of A, largest eigenvalue of A is always less or equal to eigenvalue of A11, largest eigenvalue of A11 plus largest eigenvalue of A22. Again, a very useful fact. Okay, we will shortly prove it. Okay, any idea how can we prove? Any idea how can we prove? Yeah. Okay, but before that, before proving, I mean, let us go to the proof of it and see what all we need to prove it. Okay, so one thing is given to us, it's a positive semi-definite matrix. Okay, so let us see where we will get stuck, and then maybe we require something extra to prove this. Okay, so A is positive semi-definite matrix. So that means there exists a matrix. So A can be written as now remember, just I said that it can be written as some matrix C times its C transpose, right? Can be written as A equal to C into C transpose. Okay, and since I have to deal with partitions, maybe I can partition this. See the C, okay, so let C is some matrix like this. So there is C1, there is C2. Okay, so okay, so this you assume that I am partitioning in this. So C1 size is actually size of basically what corresponding to size of A1. So it will be some the rows in C will be kind of number of rows in C will be P, right? Okay, so similarly in the rows in C2 will be n minus p. Okay, so suppose A is n cross n matrix. Okay, now what can we say about eigenvalue, largest eigenvalue of A, right? Now let us go ahead. Okay, so lambda A will be what? So lambda A, if you write, okay, will be nothing but lambda of this matrix, right? A11, A12, A21 and A22. Okay, now what? This matrix, right? This matrix, suppose I write in terms of C into C transpose, right? So this quantity is nothing but lambda of this matrix. So this is nothing but lambda 1 of C into C transpose. Very, very good. Okay, now what can we do here? Remember this lambda 1, yeah, important thing is I can also write this quantity as lambda 1 of C transpose C. Why this is true? Why this is true? Remember, maybe this you can take as a DIY. Why I can write this? Why I can write this? Okay, you see this observation. Suppose take about the matrices A, B and BA, because here it's a that form, right? C transpose and C transpose C. The eigenvalue, in fact, the all non-zero eigenvalues of AB and BA will be same. Why it will be? So, I mean, the eigenvalues of the, let me write here, in particular, the eigenvalues, the non-zero eigenvalues of AB and BA are the same. Okay, and in particular, so this is something generalized, right? In particular, if you do this, C into C transpose C, where C is given in this form, right? So the largest eigenvalue will always be same. Okay, so yeah, very good. So I mean, okay, so what next? Okay, so this is, please treat this as a DIY. Okay, very, very simple fact. Okay, just by definition of eigenvectors and eigenvalues, you can actually prove this. Now next thing is what? Now C transpose C is what? You can write this. So lambda 1 of this matrix, right? This matrix will be what? From this C transpose C is nothing but, so let me multiply these two matrices. So this is nothing but C1 transpose, C2 transpose, and then again C, right? So this is C1 and C2. Very good. So let me take this. Okay. So this will be lambda 1 of nothing but C1 transpose C1 plus C2 transpose C2, right? Just matrix product, basic. Okay. But now there is another thing, important thing to notice is this. What will be the relation between the largest eigenvalue of A plus B and largest eigenvalue of A and largest eigenvalue of B? You check that this is always greater than this. Again, I mean, this you can follow from the definition itself, definition of largest. Just see largest eigenvalue of A plus B is what? Maximum of, basically let me write, maximum of all vector x, right, where the norm is 1. So x transpose A plus B. Now this quantity is always less or equal to the maximum of, again you take norm 1, x transpose AX, right, plus maximum of vectors equal to 1, x transpose dx. Okay, so this is very, very simple, just extremal representation of largest eigenvalues. Okay, very good. So now this means that, so this quantity, okay, so now lambda 1 of this quantity is nothing but less or equal to always lambda 1 of C1 transpose C1 and plus, yeah, of C2 transpose C2. Very good. And now what? Now what? I have to prove what? The largest eigenvalue is always less than, in terms of A11 and A22. But how can he write? Oh, indeed this is true, because if you see that A1 and A22 is nothing but, so here if you see that A1, A12, A21 and A22 are nothing but, this matrix is nothing but equal to, if you, so this is equal to C into C transpose, right? So this will be nothing but, you are multiplying this matrix with its transpose, right? So basically this will be, so let me write here C1 into C transpose, right? So this is C, C1, C2 and then its transpose, right? C1 transpose, C2 transpose, very good. So this will be nothing but C1, C1 transpose, C1, C2 transpose, C2, C1 transpose and C2, C2 transpose, very good. So these two, A1 is nothing but, A11 is nothing but C1, C1 transpose, A22 is nothing but C2, C2 transpose, and we will make use of this. So this is indeed equal to lambda 1 of A11 and plus lambda 1 of A22, and this prove our result. So that implies that lambda 1 of A is always less or equal to lambda 1 of A11 plus lambda 1 of A22. Okay. Okay, so we have proved a very neat and simple fact. We will utilize this fact for proving the results on other matrices when the matrices are actually partitions. So we will utilize this result, and then we will move towards proving a very nice bound on the chromatic number of graphs in terms of its eigenvalues. Okay, and by the way, when I was defining this positive semi-definite matrices and all, there is a very nice example of positive semi-definite matrix we have already seen. What is that? That example is nothing but the Laplacian matrix of any graph is a positive semi-definite matrix. And how can we prove this? Remember that we have already seen that Laplacian matrix can be written as Q into Q transpose, right? Q into Q transpose, right? And if matrix in this form, whatever vector you multiply with X, okay, so this will be nothing but Q into Q transpose X. This will be always be greater or equal to 0. Okay, so that means all the eigenvalues of Laplacian matrix are non-negative. In fact we have seen that the rank of Laplacian matrix, if rank is n-1, then the graph is connected. That means there has to be n-1 positive eigenvalues, okay, and one eigenvalue will be 0 when the graph is basically the smallest eigenvalue of 0 when the graph is connected of Laplacian matrix. We will see about Laplacian matrix towards the end of this course. We will be having one full module on the Laplacian matrix, very beautiful matrix which is positive semi-definite matrix. Okay, so I am stopping this lecture. So thank you very much and see you in the next lecture. Yeah.